All right, another way we can find volumes is again kind of by cross section, similar to the washer method, except here we're not doing any rotating. Here it would be some solid that lies between A and B here. So on our graph, here's A and B. So we got this solid sitting here. If we were to take a slice of that, this cross section all throughout the whole shape would be the same shape, but it may not always be the same size. Like here at the ends, same shape, but a smaller piece. But it is the same shape all the way through. But it might be bigger, smaller, depending on where you take that slice. Well, since the area of that has the same shape, just depending on where you take that slice, we could get that by integrating the area of the cross section times the width of one of these cross sections from A to B. So that's kind of our goal when doing a cross section problem. Let's look at an example. This one shows a solid with a circular base. So the bottom of this is a circle. This would be what it would look like right here overhead if you were looking down on this. The parallel cross sections are perpendicular to the base. So we know that if we were to take a cross section of this, it's going to be perpendicular. And that shape is an equilateral triangle. So all throughout here are equilateral triangles that are sitting on that bottom. This overhead view would show where this triangle over here, that bottom of that triangle right here, that would be this line right here if that was sitting there. And that shape is a equilateral triangle. They want us to find the volume of the solid. Well, in order to do this, what we are going to want to do is we want to find the volume by integrating from A to B, whatever the cross-sectional area would be, in terms of our variable here, dx, since it's perpendicular to x-axis. So what we got to do now is figure out what is our limits. Well, here it looks like it's from -1 to 1. What shape is our cross section? It's an equilateral triangle. Well, let's just go with triangle for now. So we know it's the area of a triangle is 1/2 base times height dx. Now let's see if we can get a little bit more specific here. So next, what is the base and height of that triangle? Well, let's look at this overhead view again. What is the base would be this length right here. That's right here. How long is that? Well, we know from the axis to any point here, that's y. So if that distance is y, then this distance would also be y. And so our base length would be 2y. Next, let's figure out what's the height. So what would be the height? Well, if we're doing a triangle, we got to get to the peak here, and it's got to be perpendicular. Over on this picture, where we can kind of see the equilateral triangle, it would be that. Well, what is that height length going to be? Well, let's take the fact that we know it's equilateral. So if this base is 2y, which we already came up with, and it's equilateral, all these got to be 2y. If we know that they're all the same length, these are also all 60-degree angles, which means both of these are 30. And we also know that half of this would be y here. So if we look at one of these triangles right here, it's a 30, 60, 90 triangle. That's why that's 2y. And remember, in 30, 60, 90, that should be true. Whatever this length is, this one's going to be double that, so 2y. And then your third length is times square root of 3 of whatever that is. So our height would be square root of 3y, using what we know about 30, 60, 90 triangles. Okay, so now we got to integrate that. To integrate that, we can do a couple of things here. Half of 2, that's going to be just 1. our constant. We can pull out here, put it out front to make our integral a little bit nicer to work with. But we're still, and we got y times y here, it'd be y squared, but we're still stuck in the fact that we're integrating something in terms of x, but we have y here. That doesn't match. We need this in terms of x. So how do we do that? Well, we know what the equation of this circle is here. Back here, they told us the equation of this circle is a circle centered at the origin with a radius of 1 here, so that would be the equation of the circle. So now if we plug what we know y equals to in for y there, we got the equation in terms of x. So y is the same as the square root of 1 minus x squared here. And it's still squared, the equation squared here. Now we got an integral that we could solve out to find this one. And simplifying that, if you got the square root of something squared, we know that would be just turn into 1 minus x squared. Square root and the squared would cancel. And so now you got something we should be able to do. If you were doing this one like we kind of ran into with some of those other problems, I would not integrate with the square root of 3 in there because it's going to give you something you're not sure on. So just do it from -1 to 1 of our 1 minus x squared here dx, and then once you do this, then whatever this is times square root of 3 would be our answer, and it looks like as a fraction this is 4/3. So if we times that with our square root of 3, 4 square roots of 3 over 3 would be our volume here. All right, let's have you attempt one of these. So this one is a region bounded by these two parabolas. Find the volume of the solid if the cross sections are squares. So what I want you to do first, pause the video, just see if you can get a picture of what this looks like first, and then we'll go from there. All right, hopefully you've had a time to look at this graph here. You should have gotten a picture that looks something like this. Here's what the graph of y equals x squared looks like. The other one, 2 minus x squared, is also a parabola that goes through 2 here. So that one looks like that. So we're dealing with this kind of as our bottom of our graph here. And across each of these now, it coming like out of this board, if we took a snapshot of this, that would be the bottom of a square here. Where all these are the same length. So what I want you to do next now, pause this again and see if you can come up with what you think the volume equation is going to be. All right, hopefully you've had a time to attempt that. Let's see what that volume equation you came up with is. One thing we need is where are these, either from your calculator or setting these equal to each other and solving. You should have been able to come up with that if you get everything to the same side here. This would be 2x squared minus 2. And if you factor out or divide out that 2 and factor this, it looks like x minus 1, x plus 1, which would mean the two are -1 and 1 is where these intersection points are. So you should have had that. And then what is the area of the cross section? Well, that would be area of a square here, dx. So how do you find area of a square? Well, it's just whatever one of those sides are squared. So what we got to find is what is whatever the length of one of these times itself would be this area of a square. That's why it's called squaring. So what is this length here? Well, in the picture, that's the difference between these. So that would just be the top function minus the bottom function would be the answer there. And then if you solved that out, you should get the answer. And that looks like if you put it in, it comes out to be 8/3. So if you went through and did this and got 8/3 as your volume, nice job. So that's the process of those cross-section ones when you were doing that.